In today's session, we'll be learning about what is Nernst's equation and how to derive the Nernst equation under both non-standard and standard conditions from Gibbs free energy change. While doing so, we shall also see how it relates the measured cell potential to the reaction quotient and allows accurate determination of equivalent constants. So what is Nernst's equation? Walter H. Nernst, a German physical chemist, received the Nobel Prize in 1920 for his contributions to the field of electrochemistry. During his career, Nernst established an equation which correlates the ideas of chemical energy and electrical energy in a galvanic cell system. This equation is known as the Nernst equation. In electrochemistry, the Nernst equation is a general equation that relates the reduction potential of an electrochemical reaction to the standard electropotential, temperature, and activities, often denoted by concentrations, of the chemical species undergoing reduction and oxidation. Now, derivation of Nernst equation. In order to fully understand the Nernst equation, we must understand the concepts of electric work and Gibbs free energy. Let's see electric work and Gibbs free energy. Energy takes many forms. We have mechanical energy in the form of potential and kinetic energy, heat, radiant energy in terms of photons, chemical energy, nuclear energy, and electric energy. Electric work. Energy drives all changes including chemical reactions. In a redox reaction, one molecule is reduced due to gain of electrons and another is oxidized due to loss of electrons. In such reactions, the energy released due to movement of charged particles give rise to a potential difference. The maximum potential difference is called the cell potential or the electromotive force, which we call EMF. E and the maximum electric work W is a product of charge Q in coulomb and the potential delta E in volt or EMF. So W equals to Q delta E. The EMF delta E is determined by the nature of the reactants and electrolytes, not by the size of the cell or amounts of material in it. The amount of reactants is proportional to the charge and available energy of the galvanic cell. Let's see Gibbs free energy. The Gibbs free energy, which is denoted by delta G, is a quantity which allows us to determine whether or not a reaction is spontaneous. It can be defined as a negative value of the maximum work performed by a cell. If the delta G value is greater than 0, the reaction is not spontaneous. If it is less than 0, the reaction does occur spontaneously, and if delta G equals 0, then the reaction is at equilibrium. The maximum work is calculated by using the maximum EMF difference. Therefore, we have here delta G equals to minus W, which is minus Q delta E. A redox reaction equation represents definite amounts of reactants in the formation of also definite amounts of products. The number n of electrons in such a reaction equation is related to the amount of charge transferred when the reaction is completed. Since each mole of electron has a charge of 96,485 C, known as the Faraday's constant F, Q equals to NF. The Faraday constant is a units conversion factor, which is F equals to NAQ, where Na is the Avogadro's number and Q is the fundamental electron charge. The electrochemical potential E associated with an electrochemical reaction is defined as the decrease in Gibbs free energy per coulomb of charge transferred, which leads to the relationship delta G equals to minus NF delta E. This is under general conditions. At standard conditions, delta G naught equals to minus NF delta E naught. Hence, when E naught is positive, the reaction is spontaneous, and when E naught is negative, the reaction is non-spontaneous. Now let's look at the general Nernst equation. The general Nernst equation correlates the Gibbs free energy change, delta G, and the cell potential or EMF of a chemical system. From thermodynamics, the Gibbs energy change under non-standard conditions can be related to the Gibbs energy change under standard conditions via the equation delta G equals to delta G naught plus RT ln Q. Let's call this equation number 1. Now for the reaction, reactants A plus B, which gives rise to C plus D, the reaction quotient is Q equals to the product of the concentrations of C and D by the product of the concentrations of A and the B. It has been shown that delta G equals to minus NF delta E and delta G naught equals to minus NF delta E naught. So substituting these equations to equation 1, we get minus NF delta E equals to minus NF delta E naught plus RT ln Q. Let's call this equation number 2. Now divide both sides of this equation 2 by minus NF. We have now delta E equals to delta E naught minus RT divided by NF ln Q. Now let this be equation number 3. This equation can be rewritten in the form of log base 10, which is delta E equals to delta E naught minus 2.303 RT by NF log Q, which is equation 4, where R is the universal gas constant at 8.314 joules per mole per Kelvin. T is the temperature in kelvins. Q is the reaction quotient and F is the Faraday constant, which is 96,485 coulombs. This is known as the generalized Nernst equation, which is at non-standard conditions. This equation allows us to calculate the cell potential of any galvanic cell for any concentration. And let's look at the Nernst equation at 25 degrees Celsius, which is 298 kelvins. At any specific temperature, the Nernst equation, which is derived at equation 4, can be reduced into a simple form. So at standard temperature, which is T equals to 298 Kelvin, which is 25 degrees Celsius, the 2.303 RT by F term equals to 0.0592 volts. And this equation, which is the generalized Nernst equation, turns into delta E equals to delta E naught minus 0.0592 V by N of log Q. Let's call this equation number 5. Now this is the Nernst equation at standard conditions. This equation indicates that the electric potential of a cell depends upon the reaction quotient Q of the reaction. As a redox reaction proceeds, reactants are consumed and thus the concentration of reactants decreases. Conversely, the product's concentration increases due to the increase in the product's formation. As this happens, cell potential gradually decreases until the reaction is at equilibrium, at which delta G equals to 0. At equilibrium, the reaction quotient Q equals to KEQ, where KEQ is the equilibrium constant. Also at equilibrium, delta G equals to 0 and delta G equals to minus NF delta E. So, delta E equals to 0. Therefore, substituting Q equals to KEQ and delta E equals to 0 into the Nernst equation, we have 0 equals to delta E naught minus RT by NF ln KEQ. Let's call this equation number 7. At standard conditions, the equation number 7 simplifies into 0 equals to delta E naught minus 0.0592 volts by N log KEQ. So this equation can be rearranged into log KEQ equals to N delta E naught by 0.0592 volts. So this equation indicates that equilibrium constant KEQ is proportional to the standard potential of the reaction. Specifically, when K is greater than 1 and E naught is greater than 0, reaction favors products formation. And when K is less than 1 and E naught is also less than 0, reaction favors reactants formation. So that's how we derive the Nernst equation. Let's look at the application of this equation. The Nernst equation has a physiological application when used to calculate the potential of an ion of charge Z across a membrane. This potential is determined using the concentrations of the ion both inside and outside the biological cell. The Nernst equation makes it possible to calculate the theoretical resting membrane potential of a cell membrane if the ratio of the internal and external ion concentrations is known. Membrane potential, also known as the transmembrane potential or membrane voltage, is the difference in the electric potential between the interior and the exterior of a biological cell and is essential for many physiological processes. With respect to the exterior of the cell, typical values of membrane potential range from minus 40 millivolts to minus 80 millivolts. The membrane potential has two basic functions. First, it allows a cell to function as a battery, providing power to operate a variety of molecular devices embedded in the membrane like electrogenic transport proteins, which are the secondary active transporters. Second, in electrically excitable cells, such as neurons and muscle cells, it is used for transmitting signals between different parts of the cell. Signals are generated by opening or closing of ion channels at one point in the membrane, producing a local change in the membrane potential. This change in the electric field can be quickly affected by either adjacent or more distant ion channels in the membrane. These ion channels can then open or close as a result of the potential change, reproducing the signal. The flow of an ion through a membrane channel protein is driven by the electrochemical gradient for that ion. This gradient represents the combination of two influences, the voltage gradient and the concentration gradient of the ion across the membrane. When these two influences just about balance each other, the electrochemical gradient is 0 and there is no net flow of the ion through the channel. The voltage gradient, which is the membrane potential at which this equilibrium is reached, is called the equilibrium potential for that ion. It can be calculated from the Nernst equation we just derived. Here, we can reproduce the Nernst equation as V equals to RT by ZF ln CO by Ci, where V is the equilibrium potential in volts, that is the internal potential minus the external potential. CO and Ci are the outside and inside concentrations of the ion respectively. R is the gas constant, which is 2 calories per mole per Kelvin. T is the absolute temperature in kelvins. F is the Faraday's constant, which is 2.3 into 10 to the power 4 calories per volt per mole. Z is the valence or the charge of the ion. Here the Nernst equation is derived as follows. A molecule in solution, which is a solute, tends to move from a region of high concentration to a region of low concentration simply due to the random movement of molecules, which results in their equilibrium. Consequently, movement down a concentration gradient is accompanied by an unfavorable free energy change. Here delta G is greater than 0. The free energy change per mole of solute moved through the membrane, which is we call delta G concentration, is equal to minus RT ln CO by Ci. If the solute is an ion, moving it into a cell across a membrane whose inside is at a voltage V relative to the outside will cause an additional free energy change per mole of solid moved of delta G volt equals to ZFV. At the point where the concentration and voltage gradients just balance, delta G concentration plus delta G volt equals to 0. And the ion distribution is at equilibrium across the membrane. Thus, ZFV minus RT ln CO by Ci equals to 0, and therefore V equals to RT by ZF ln CO by Ci equals to 2.3 RT by ZF log base 10 CO by Ci. For a univalent ion, 2.3 RT by F equals to 58 millivolts at 20 degrees Celsius and 61.5 millivolts at 37 degrees Celsius. V equals to plus 61.5 millivolts for CO by Ci equals to 10, whereas V equals to 0 for CO by Ci equals to 1. The potassium ion equilibrium potential, which is denoted by Vk, for example, is 61.5 log base 10 of the outside concentration of potassium by the inside concentration of potassium ion in millivolts. At Vk, there is no net flow of potassium ion across the membrane. Similarly, when the membrane potential has a value of 61.5 log base 10 outside concentration of sodium ions by the inside concentration of sodium ions in millivolts, the sodium ion equilibrium potential is V sodium. There is no net flow of sodium ion. For any particular membrane potential, Vm, the net force tending to drive a particular type of ion out of the cell is proportional to the difference between Vm and the equilibrium potential for the ion. Hence, for potassium ion, it is Vm minus Vk, and for sodium ions, it is Vm minus Vna. Now, we shall conclude today's section with the following points. The Nernst equation is perhaps the most important equation in the field of electrochemistry. Secondly, the Nernst equation relates the reduction potential of an electrochemical reaction to the standard electrode potential, temperature, and the activities of the chemical species undergoing the reduction and oxidation reactions. Thirdly, it can easily be derived from the standard changes in Gibbs free energy associated with an electrochemical transformation. Next, the generalized Nernst equation gives us a means of calculating the cell potential of any galvanic cell with any concentrations. And lastly, the standard Nernst equation for standard conditions indicates that the electric potential of a cell depends upon the reaction quotient Q of the reaction. At equilibrium, the equilibrium constant Keq is proportional to the standard potential of the reaction, and it can be used to calculate the membrane potential across a cell membrane if the ratio of the internal and the external ion concentrations is known.